Welcome to The Explainer. Today, we're unpacking a codebase that is, well, it's beautifully bizarre. It literally fuses golden ratio mathematics, cryptography, and emojis.
Yeah.
Emojis. It combines all of that into a highly stylized distributed network protocol. We're looking at a system that completely reimagines how software architecture can look, feel, and operate.
So right off the bat, we run into the system's most eccentric core rule. One event emits one emoji only. Think about that for a second. Instead of those massive, dense text log files we're all used to staring at, this system communicates its entire state through a stream of emojis. It's not just a quirky add-on, it's actually the foundational design choice. Here's our roadmap for today's explainer. We'll start with the anatomy of a jewel, move into the Phi kernel architecture, look at forging the Dragon Flame, check out the enlightened network scanner, explore the Hive Federation, and finally wrap up with reaching collective coherence. Let's get right into it. Section 1, Anatomy of a Jewel, the atomic unit. We've got to start at the absolute micro level with the system's fundamental building block. So there's this data structure, appropriately named a jewel. It's initialized with an ID, a mode, and an integer vertex. But the magic is really in what it does with that vertex. It extracts specific bit values, which it calls A, B, and C, using bitwise right shifts and masking. And remember that emoji rule? Every single time one of these bits is checked or a delta is validated, the code emits a unique emoji to the terminal. It's exactly like a tiny gear turning in a watch. Imagine debugging your bitwise logic using only smileys. Wild, right? But don't let the smileys fool you. Underneath all that quirkiness is some incredibly rigorous engineering. The developers aren't just playing around in Python here. They've mirrored this exact esoteric logic in a highly efficient C99 implementation. We're talking serious, memory-optimized routines where a jewel state is packed super tightly into just a few bytes. Moving on to Section 2, the Phi kernel architecture, connecting the jewels. How exactly do these individual jewels interact and evolve over time? Well, they're grouped into what's called a Phi kernel. You can think of the Phi kernel as a sort of localized container, or even a micro-universe. It's responsible for moving up to 64 joules forward in time through a specific method called a tick. During one of these ticks, integer deltas are applied to the joules to change their states, mutating their vertices using bitwise XR operations. Now, you might be thinking this sounds like total chaos, but it's really not. The joules are bound by incredibly strict edge constraints. Before a tick can actually commit and permanently change the kernel state, it has to verify these edges. Notice the strict matching logic. Joules might need to have matching A bits, or their bits might need to XOR properly against each other. Basically, if the mathematical topology doesn't hold up perfectly, the tick is completely rejected. So, with this very delicate architecture constantly mutating data across all these joules, we have to ask a pretty big question. How on earth does this system securely identify and protect these states from tampering? That brings us to Section 3, Forging the Dragon Flame, Golden Ratio Cryptography. This is where the math gets absolutely fascinating. The security process goes through 4 really strict steps. Step 1, it generates a standard SHA-256 deterministic digest from the data. Step 2, it permutes those bits, literally walking backwards through the byte array and mixing them up. Step 3, it folds them using golden ratio math. And Step 4, it spits out a base 62 flame string. That string acts as a highly compressed, totally unique cryptographic signature of the system's state. But the real standout here is Step 3, the hex fibbin fold. The system takes specific hexadecimal representations of phi, the golden ratio, defined in the code as 0x00010000. It uses this constant and its mathematical inverse to cross-multiply and mix the bytes of the hash. It is literally weaving the geometry of the golden ratio directly into the cryptographic integrity of the network. How cool is that? And, of course, it gets weirder. This cryptographic output is paired with something called worm body rhetoric. It's an eccentric function that prints out colorful emoji phrases based on the A, B, and C bits of a given joule. Depending on the states, you might get a worm emoji representing a witness, a red circle for a union, or a blue circle for motion. It completely transforms a dry cryptographic hash check into a piece of abstract digital art. All right, Section 4, the enlightened network scanner, finding the hive. Let's look at how these secure kernels actually find each other out in the wild. Using standard Python networking sockets, the enlightened scanner aggressively probes entire subnets looking for active peers.
It uses a thread pool executor to rapidly connect potential IPs across specific ports, measures the latency in milliseconds, and builds host signatures. It's kind of funny to see such a highly concurrent, entirely practical networking tool wrapped up in this sort of mystical terminology, isn't it? Once it finds those peers, it bundles all that crucial discovery data into a network scanning payload. This includes the target subnet, chunk IDs, tick counts, and the host signatures themselves. But here's the kicker. The entire payload is cryptographically sealed using that Dragon Flame we just forged. This guarantees absolute data integrity across the wire. If even a single bit is altered in transit, the golden ratio math in the Dragon Flame signature will instantly catch it and invalidate it. Which leads us right into Section 5, the Hive Federation, Distributed Consensus. Now that the nodes are discovered and verified, they're brought into this distributed consensus layer. The Federation manages entries super strictly via a public signed invite. When a node tries to join, the Federation checks its cryptographic signatures and expiration times. But the absolute most brilliant part is how it assigns weight. It uniquely binds each node's mathematical weight by the inverse of the golden ratio, labeled as PHI_INV. So a node can't just jump in and claim maximum influence. The network mathematically limits its weight using the exact same geometric constants that secure its cryptography.
And staying totally true to that terminal rule we talked about earlier, every single acceptance or rejection of a node emits a specific divergent emoji to the console. Expired signature, node ID mismatch, wrong vector dimension, each one pulses a specific visual symbol. Imagine being the network admin for this thing. Instead of scrolling through walls of dense error text, you're just watching a rapid-fire, matrix-style stream of symbolic rejections and acceptances.
Finally, Section 6, Reaching Collective Coherence, the final math. Once all the nodes are accepted, what exactly are they doing together? What is the ultimate purpose? Well, the Federation combines the data of every accepted node to compute a massive 144-dimensional collective vector. It achieves this by taking the internal vector of each individual node and multiplying it by that golden ratio bounded weight we mentioned. It essentially merges all these floating point values into one giant, unified state that represents the entire distributed network. Once that 144-dimensional vector is locked in, the system calculates overall coherence. It does this by taking the square root of the sum of the squares of this vector, which basically gives you the magnitude of the network's collective state. After all that math, it outputs a pristine JSON object called Hive Federation Receipt. This receipt holds the payload hashes, the node count, and that final coherence number, all neatly cryptographically signed. So after unpacking all of this, I want to leave you with something to chew on. If secure network consensus can genuinely be powered by golden ratio mathematics and diagnosed entirely through a stream of emojis, what other bizarre aesthetic paradigms could revolutionize how we code? It really makes you wonder if our traditional ways of writing and logging software are just one tiny possibility in a much wilder universe of design. Thanks for joining me on The Explainer today, and I hope this sparked some curiosity.
All right, let's jump right into this. Today, we're diving into a highly unusual, heavily stylized codebase to uncover the complex constraint-solving engine hidden beneath its, well, very poetic layers. At first glance, the document we're exploring looks like a chaotic mix of art and code. But as we peel back the layers, you're going to see some truly brilliant engineering at work here.
So what exactly happens when you mix cryptography, the golden ratio, and emojis? You might think it's just an eccentric programming puzzle or maybe some art project that accidentally involves code. But what we're actually looking at is a deeply architectural mystery. We're examining a hybrid protocol that seamlessly blends high-level abstract concepts with bare metal memory management. It's a fascinating look at how mathematics, specifically the golden ratio, can be weaponized, actually, scratch that, harmonized, to build incredibly secure, decentralized network structures.
Take a look at this bizarre surface layer. We've got a Python file called Joule model that literally spits out emojis for terminal logging. Instead of your standard boring text logs saying process started or data loaded, this codebase emits a whole visual language of worms, keys, moons, and gems. But don't let the playful facade fool you. Every single one of those emojis corresponds to a highly specific state transition happening under the hood. To decode this absolute spellbook of a codebase, we kind of need to translate its strange terminology into standard computer science concepts, starting from the micro-level building blocks. The creator of this code didn't just write functions, right? They built an entire mythology. But my goal here is to bring this back to reality for us. So when we see terms like dragon flames or enlightened scanners, we're actually looking at robust hashing algorithms and network discovery protocols. Let's break these down one by one.
Section 1. Anatomy of a joule. Nodes and state machines.
Let's see how this builds the absolute foundation of the network. If we strip away all that artistic flair for a second, a joule is essentially just a network node. It's a state machine, evaluating simple bit logic. Every joule holds a unique ID, an operating mode, and a vertex integer. It exposes methods to read specific bits, bit A, bit B, and bit C, and it strictly controls how those bits can be altered using bitwise XOR operations. It's a microstate manager that forms the fundamental atom of this entire universe.
Then we have the phi kernel. Think of this as the strict conductor of the orchestra. It takes in a collection of these joules and verifies their connections through specific constraints. The kernel doesn't just let joules change their states willy-nilly. No way. It bundles them up, takes their proposed changes, which it calls deltas, and meticulously projects what the network would look like if those changes were applied. If any single rule is broken across the edges connecting these joules, the kernel rejects the entire operation, period. So the big takeaway here is that underneath all those eccentric names, the kernel is rigorously checking mathematical relationships before accepting any changes. For example, the FPJ_A_match constraint demands that two connected joules must share the exact same value for their first bit. The FPJ bridge is even more fascinating. It requires a Hamming weight greater than 0. That mathematically guarantees there is some measurable difference, meaning they aren't completely identical, between the vertices of two bridged nodes. It is pure strict constraint programming.
And honestly, this right here brilliantly illustrates the juxtaposition of the codebase. Vibrant, emoji-filled Python wrappers resting directly on top of rigid, lightning-fast C code structs. On one side, you see the Python code orchestrating the logic and printing out those playful visual logs, but on the other side, you have the underlying C implementation, managing fixed-sized arrays, raw memory blocks, and bitwise operations to ensure maximal performance and absolute memory safety. It is a gorgeous marriage of high-level art and low-level performance.
Section 2. Cryptography and Dragon Flames, the golden ratio hash.
Now that we've got the nodes down and understand how their states are managed, let's explore the cryptographic magic that actually secures them. This specific hexadecimal constant is derived from phi, the golden ratio, and it forms the mathematical bedrock of their custom hashing algorithm. In decimal form, this ties back to the mathematical constant of 1.618, but it's encoded as an integer for high-speed bitwise arithmetic. The author of this protocol didn't just want standard security. They wanted mathematical harmony embedded into the very foundation of the cryptography.
You can actually see it right here in the hexfib file. The code uses bitwise shifts and these golden ratio constants to deterministically fold data. The hexfib fold value function takes a left and right integer, XORs them together, and then multiplies them against these inverse phi constants. This creates a highly deterministic yet beautifully chaotic avalanche effect on the bits. This is custom, esoteric cryptography at its absolute finest.
So, when we hear a wild term like Dragonflame, we now know it isn't actual magic. It's a multi-step cryptographic signature binding a SHA-256 hash with those phi-based mathematical constants. It takes a seed string, which could be the state of a joule, hashes it securely, folds it through that golden ratio math we just looked at, and then spits out a compact, base 62 encoded string. This flame acts as a totally immutable fingerprint for the data.
Section 3. The Enlightened Network Scanner, probing the void.
With our state machines and cryptography locked in, the code base suddenly shifts gears and focuses outward to the real world. This scanner class reveals that this entire system is designed to look for other active participants on a network. It isn't just meant to sit there and run in isolation on a single machine. No, it is actively reaching out, probing the darkness of the internet, trying to find other nodes that speak its highly specific, mathematically harmonized language.
Basically, it acts like an IP subnet discovery tool, meticulously pinging addresses and measuring response times. But here is the genius part. It converts those foreign connections into new joules. It maps the latency and the open ports into a mathematically sound state, generating a host signature. Finally, it takes all these newly discovered nodes and seals them into a Genesis kernel, effectively birthing a brand new local network map from the raw data of the internet.
As we can see in this block of code, the scanner utilizes threaded executors to map out the network's topology rapidly and build its foundational Genesis kernel. You can see the thread pool executor firing off concurrent probes with a strict 0.8-second timeout. It's aggressively, yet elegantly, scanning chunks of the network to find peers that can form the basis of its complex constraint-solving matrix.
Section 4. The High-5 Federation. Decentralized Coherence. This brings us to the grand reveal, the macro-level purpose of everything we've just decoded. We've seen the jewels, the cryptographic flames, the network scanner, and we realize it's not just a programming puzzle. It's a fully functional framework for a decentralized peer-to-peer network evaluating its own collective state. The entire goal of this esoteric software is to bind distributed nodes together into a federation, ensuring they can communicate securely, trust each other through cryptographic invites, and work together to calculate their overall harmony.
Now, obviously, security here is absolutely paramount. Nodes can only join this federation through a rigorous, public-signed invite system. Notice how heavily guarded these invites are. They are restricted to specific node IDs, they have strict time-to-live expiration limits to prevent replay attacks, and their influence in the network is mathematically bounded by, you guessed it, the inverse phi constant. The whole shebang is locked down with an HMAC SHA-256 signature. Once everything is connected, the network calculates its coherence, mathematically evaluating how in sync all these diverse distributed nodes actually are. It takes the vector states of every single node in the federation, weights them based on their authorized influence, and computes the sum of the square roots of those elements. This isn't just basic data transfer. This is the network calculating a numerical value of its own collective harmony.
Look really closely at how the code finalizes this whole event. It computes the coherence we just talked about, bundles it with the current timestamp and the payload hash, and spits out a cryptographic receipt. This receipt acts as ironclad proof of the network state at a specific moment in time. The divergent pulse function fires off, printing the final receipt emoji and sealing the entire interaction in a mathematically verifiable, beautifully logged package.
All of this leaves us to wonder, is this esoteric architecture the blueprint for an entirely new kind of secure, artistic internet, or is it just a fleeting masterpiece of code? We've seen how strict C-structs, the golden ratio, and simple emojis can come together to build a robust, decentralized federation. It absolutely challenges our very definition of what code can look like and how networks can operate. What do you think? Thank you so much for exploring this with me today, and I really hope you walk away seeing the art hidden inside the architecture.
All right, let's jump right into this explainer, because today we are looking at something completely wild. Seriously, it's structurally magnificent but totally bizarre. Imagine a highly sophisticated, mathematically driven distributed network. But here's the catch. Instead of spitting out standard computer logs, this whole system tracks its state by, get this, emitting strings of emojis. Yeah, you heard me right. That's the actual architecture we're unpacking today. A system officially documented as the Divergent Emoji Network. So it really begs the question, doesn't it? What exactly happens when you smash together serious, decentralized network architecture with, well, poetic obfuscation? On the surface, the source code we're about to explore just looks completely chaotic. I mean, it's this weird visual language made up of worms, moons, and colored circles. But right beneath that crazy surface, there is a rigid, mathematically obsessive underbelly. It's this beautiful tension between utter chaos and strict order, and honestly, I am absolutely thrilled to guide you through how this thing actually works. Here's how we're going to tackle this. First, we'll decode that strange, esoteric syntax. Then we'll dig into the foundational jewels and the phi kernel. After that, we'll unpack its totally unique cryptography. And finally, we'll trace how it actually scans and achieves consensus across a massive network. Okay, so kicking things off with part 1, decoding the esoteric syntax. Let's start stripping away all the poetic weirdness of this source code so we can actually see the raw logic underneath. Think about the worm body rhetoric local function. If you just read it, it sounds like some bizarre poem about a worm, a union in motion, complete with literal red and blue circle emojis. But mathematically, it is just deliberately masking a very standard bitwise XOR operation. Basically, it's checking the binary states of A, B, and C to calculate a value called tau. If the bits flip, boom, the color of the emojis changes. So what we have here is literally a binary state machine just masquerading as digital art. To help us navigate all this madness, I've put together a sort of decoder ring based on the source files. And this is crucial. Every single piece of fantasy terminology here translates directly into a very real standard networking or cryptographic concept. That worm body, it's just state string generation. The Dragon Flame, actually a deterministic SHA-256 hash. The Enlighten scanner is simply a subnet socket scanner, and the Genesis kernel is just the initial network state map. When you actually translate the vocabulary, it hits you. We are looking at a very serious piece of network infrastructure.
Moving right along to Section 2, Joules and the Phi kernel. Let's zoom in a bit and see how this system builds at the micro level with its foundational data blocks, which the code refers to as joules. The setup of the code brilliantly illustrates the dual nature of the entire system. On one hand, we've got this chaotic, emoji-emitting Python script powering the network scanner, but right next to it, a super strict C99 header file. The Python code is actually backed by an extremely optimized, explicit, memory-managed C backend. The foundational data structures, those joules, are strictly defined down to the absolute byte in C. That tells us the creator cared deeply about raw computational performance, even with that playful exterior. But here is where things get truly obsessive. The entire architecture is built around the golden ratio, mathematically denoted as phi. In the system's fixed point math, it's defined as the hex value 0x000019E37. And this specific mathematical constant isn't just a fun little gimmick. It literally dictates everything in the system. We're talking from how the low-level bits are folded in the cryptographic hashes, all the way to how network nodes are weighted during consensus. This recurring use of the golden ratio proves this isn't just random, hacked-together code. It is a meticulously calculated, almost obsessive architecture. All right, on to Section 3, Cryptography of the Dragon. Let's shift gears to the mid-level architecture and figure out how this network actually secures and verifies its data payloads using what the code calls the Dragon Flame. Take the Dragon Flame 16 function, for instance. The system uses this to seal data. And while Dragon Flame sounds magical, it actually relies heavily on a deterministic digest function. It's essentially taking data, passing it through a really strict hashing algorithm, folding it, and then spitting out a secure signature. To break the cryptography down really simply, here is the actual equation operating behind the scenes. A Dragon Flame is just a rigorous SHA-256 hash, which is then mathematically folded using bitwise operations tied to that phi constant we just talked about, and then finally scrambled through a base 62 permutation. So, in short, behind that whole fantasy naming convention lies a very standard, highly impenetrable cryptographic wall. There is absolutely no way you're forging a payload on this network. Which brings us to Section 4, Network Scanning and Propagation. Now we escalate to the macro level. How on earth does this code break out of a single, isolated machine and begin sweeping across a wide network? Tracing the system's lifecycle sequentially shows us exactly how a subnet is mapped, measured, and absorbed. First up, targeting. The Block 0 scan controller defines the specific subnets it wants to hunt in. Second, probing. The Enlighten scanner reaches out and tests socket connections for latency. Third, packaging. If a valid host actually responds, it gets bundled into a network scanning payload. And finally, bootstrapping. All these payloads are merged together to build the Genesis kernel, which basically maps out the entire local network state. And honestly, the specific details of the scanning protocol are incredibly revealing. It initiates standard TCP socket stream connections, sure, but it uses this ruthless timeout protocol of exactly 0.8 seconds. If a node doesn't respond instantly, it's dropped. It records the precise latency in milliseconds, binds app physical networking data to a logical Joule vertex, and then cryptographically seals the whole package. So underneath all those cute emojis, what we actually have is a highly capable, pretty much weaponized network scanner aggressively hunting for live hosts. And that brings us to our fifth and final and probably most complex architectural layer, the High Federation consensus. How do all these scanned and participating nodes actually agree on a shared reality? Well, joining this network is definitely not trivial. The process follows an incredibly strict life cycle for a public signed invite. At time 0, an invite is generated using a master Hive secret. Almost immediately, the network verifies the cryptographic HMAC signature. Think of it as a tamper-proof digital wax seal. Then it checks the exact timestamp to make sure the invite hasn't expired past its time to live, or TTL seconds. It is only if all these rigorous security checks pass that the new node is accepted, at which point its mathematical weight in the network is recomputed. If we drill down into the phi node data class, specifically that weight property, we see something wild. Individual nodes are mathematically bounded by phi inverse, which is the inverse of the golden ratio.
So get this, not only is phi used to encrypt data, it's actively used to calculate how much voting power or influence a single machine has within the wider federation. The math literally dictates the network's politics.
Let's contrast these two states to make the codebase's ultimate goal crystal clear. A standalone Joule node is just an isolated entity. It's got its basic A, B, and C bitwise state, but absolutely no network influence. But when it joins the network, it becomes part of the High Federation, a collective vector. It is no longer isolated. It becomes part of a merged reality represented by a massive, heavily weighted float array. The entire goal of the system is moving from meaningless isolated data points into a single, cohesive, shared network state. And that merged reality takes a very, very specific shape. 144. That is the fixed dimension of this collective vector in the source code. It represents a 144-dimensional space. The system is constantly computing the square root of the sum of the squares across these 144 dimensions to calculate what the code literally labels as network coherence. Basically, it's trying to mathematically prove that the entire decentralized network is operating in absolute perfect harmony. Which leaves us with this final, incredibly provocative thought. We've seen the aggressive network scanning, the highly optimized C99 memory management, the golden ratio cryptography, and of course, the emojis. So, what is this? Is it just a highly elaborate digital art project? Is it a brilliant conceptual prototype for some future decentralized infrastructure? Or, given its aggressive scanning and intense obfuscation, are we actually looking at a new breed of highly stylized malware? Whatever its true purpose is, one thing is for sure. It is built with deliberate, coherent weirdness. Thank you so much for joining me on this explainer, and keep exploring out there.